move to the last speaker of this first session, and is Trygve, also coming from the Institute for Theoretical Astrophysics in Oslo, and you will talk about leakage correction. Please, Trygve.
Yes, leakage corrections. So this is our approach to leakage corrections in BeyondPlanck. So just a bit of background. This is the LFI signal as we see it on the sky for the three different frequency bands, the 30, 44, and 70 gigahertz for the temperature and the polarization signals on the right here. And the thing is, we don't observe the sky at sharp frequencies, but rather over a range of frequencies, which is determined by the bandpass profile. And in addition to that, the satellite doesn't see the sky at one single point at a time, but rather over some spatial distribution given by the beam shape. And for example, the bandpass here is something that is calculated on the ground prior to commission, and it's therefore definitely has uncertainties tied to it. And if these aren't properly controlled, that will lead to leakage in our data. And I'll come back to the description of that. But this is a picture of the Planck focal plane where we see these feed horns. Within all of these feed horns are detectors. And as you can see, even though this is the LFI instrument, Marco has talked about this, but there aren't three feed horns. There are several, and several detectors. So each of these detectors have a bandpass profile, and this is the average bandpass profile. And you can see that they extend over some frequency range, and they vary over that range. And in addition to this, this is an example of beam profiles and how they're not necessarily perfect Gaussian distributions. So what is leakage and how does it occur in our data? So as I said, we have several different radiometers, and we often want to combine these radiometers to reduce the noise. And the sky looks slightly different to every radiometer, and this is categorized by things such as the beam and the bandpass. But when we solve for these maps the frequency maps during map making, we assume every radiometer to see the same sky. So these bandpass and beam differences must be accounted for. And during map making, any discrepancy between these radiometers is interpreted as noise. And for our algorithms, when solving for correlated noise, this leads to a sort of dolphin morphology, where discrepant signal along the galactic plane is downweighted according to the scanning strategy over the sky. So you get these kind of morphology, all kinds of sea creatures here. And in order to fix this, we want to parameterize the leakage in some mathematical way. And we therefore introduce a new parameter to quantify it in BeyondPlanck and the whole Gibbs loop system. And we therefore have this delta S leakage per radiometer and in time domain. So this is a measure of the leakage per detector. And that's the difference relative to the mean of the sky per radiometer. So we want to subtract this from every radiometer before combining. And this is how it's defined, where we subtract, or it's the difference to the mean of all the radiometers, J. And this is one of several quantities that we correct for in BeyondPlanck, and Matthew just talked about the far side lobes here, for example. So now that we have a handle on the actual leakage, we want to parameterize the correction. So how do we actually correct the leakage? And our approach is very simple. It's a linear shift in frequency, where tau here is the bandpass profile, nu is the frequency, and this is a delta shift in frequency space. So it looks something like this. For a bandpass profile such as the 70 gigahertz average here, we simply shift it back and forth. And we do this in several ways. We actually decompose it in BeyondPlanck so that we get for the full ensemble of all the radiometers within one band, we have an absolute band average shift and also relative shifts within that. So a shift for each radiometer. And this approach isn't necessarily ideal or perfectly physically motivated, but it is definitely effective. And this there are uncertainties related to, for example, the ends and the tails of these, which we see here. For example, the profile doesn't go all the way down, and there could perhaps be missing signal here. So there's all kinds of different approaches that we could do this, do in fixing this and improved upon in the future. So now that we have a parameterization of the correction, how do we estimate that quantity? And we do that using a Metropolis Hastings sampler. And for everyone familiar with the Metropolis Hastings sampler, that means that we require an error statistic. And in BeyondPlanck, we use spurious maps, which is a measure of how different a detector is from the mean. So for the signal per detector J, we solve for the TQ new signal, but we also add this spurious map term here. And that means that in map making, we also, for a 3 detector case, that means getting 2 spurious maps. For a 4 detector case, we would get an additional one. However, we only do this as an error statistic when we're doing the bandpass corrections. So we throw away these TQUs that we calculate here because that would give us some excess noise if these were the actual TQUs that we used. So these are examples of the spurious maps that are calculated internally in Commander, and only for the error statistic. And this is without applying any corrections to each of the radiometers. So we get this large foreground type signal here that we attempt to minimize throughout the pipeline, and this is the final result in BeyondPlanck. So we definitely improve that and get a better result on the bandpass internally. So there are several challenges that we face when applying bandpass corrections, and bandpass effects influence many analysis steps. And for example, the absolute corrections that we apply, for example, to the 30 gigahertz, or if we would the 70 gigahertz, shifting it up and down, would definitely be or could be that degenerate with foreground parameters such as the thermal dust beta that would, if we shifted it, perhaps prefer a steeper value. So we only apply absolute shifts to the 30 gigahertz band, and that's a 0.3 gigahertz, which is motivated by the Planck collaboration's results. So over to our final results and how what the corrections turn out to be in the BeyondPlanck pipeline. And these are the posterior bandpass corrections. So for every radiometer here on the x-axis, this is the bandpass shift in gigahertz. And as you can see, all of them are within 1 gigahertz almost. The 30 gigahertz band here, the 44 and the 70 gigahertz, the error bars that you see here is just because these are determined of the foregrounds. And on the 70 gigahertz band, the foregrounds are much weaker. And we see here the 0.3 absolute shift. And we also, all of the internal corrections average out to 0. So that's just a deterministic solution here that we don't we don't introduce any new degrees of freedom to the system by doing it this way. However, there's one outlier here that you might have caught already, and that's the 18M radiometer in the 70 gigahertz. So what is the deal with that? And if we look a bit closer and investigate the bandpass profiles for the 70 gigahertz band and zoom in to the high frequency tail, this is a bit of a messy plot, but the 18M detector that we're interested in is the black solid line here. And you can see some strong standing waves here on the far tail that might have been induced by the measuring equipment prior to commission. And you see that there's the other bands see some sort of or would prefer some higher sensitivity here that the 18M detector sees here. So that this bandpass profile prefers a shift in the negative direction does actually make sense, but it also is most likely a measurement or an uncertainty. So not necessarily something that we would want to include. And these are the leakage corrections that we end up with when we bin them into maps for all of the radiometers. And we, for example, in the 30 gigahertz here, it's most easy to see because the foregrounds are the strongest, and we see this temperature to polarization leakage that we actually remove with this approach. And for the 30 gigahertz, that is the strongest where the strongest foregrounds are. And I haven't touched too much on the beam mismatch corrections, but if we see how, for example, in the 44 Q band here, and zoom in to the southern hemisphere, we can look at the small scale differences here. And this is a zoom in of the same area in the CMB map, of course, with a different color scale here. And this is the leakage map that we just looked at. And there is obvious correlation between these two. And this is simply because of the beam, we're seeing the CMB slightly differently. And this discrepant signal is then removed. So that is it for me. Thank you for the money. And are there any questions?
Thank you, Trygve.